In 10.5, we're going to continue to look at different tests to determine convergence or divergence of a series. This is a fairly short section. We're going to cover two comparison tests. In a comparison test, what you do is you find a series to compare to your given series. You're going to choose a series in which you know whether it diverges or converges. So let's look at our first test, the comparison test. Let's say that we have two series, a sub k and b sub k. Now here we're just going to concern ourselves with series of positive terms, but then later on we're going to look at series that have negative terms, series that alternate negative positive. The first case would be if your a sub k is less than or equal to your b sub k. So b sub k would be like the larger series. In this case, if the larger series b sub k converges, then the smaller series a sub k will converge. Let's look at what that means in a graph. So let's say that we have our larger series b sub k. For a series to converge, what you're saying is that the terms are getting smaller and smaller and smaller so that the sum approaches some number. So this graph that I'm drawing here could represent a series that converges. If I connect the dots and write this as a function, I could get a series that looks like this. So this would be my b sub k. Now a sub k is larger than or equal to, so an example of an a sub k would be this following series in red, connecting the dots. You can see that if b sub k converges, it's forcing the smaller series a sub k to also converge. Let's look at criteria 2. Let's say that b sub k is less than or equal to a sub k. So b sub k in this case is the smaller. Well, if the smaller b sub k diverges, then the larger a sub k will diverge. And we can illustrate this with a graph. So remember, b sub k is smaller, b sub k diverges. Diverging means that as you add up your terms, they don't approach a number. So in essence, you can think of it as getting larger and larger and larger. So if I create a graph or a curve for my b sub k and show that it diverges, a sub k is larger. So you can see by this illustration that if our b sub k, smaller one, diverges, the a sub k, larger one, will also diverge. So the key is to pick series to compare in which you know whether they diverge or converge. So we often use things like a p-series. P-series, very easy to determine whether the series diverges or converges. Geometric series. So let's look at what I mean by example 1a. I have this series, 1 over k to the 3 halves plus 1. Now I can see that if I get rid of the plus 1, I'll have a p series, and since p is 3 halves, which is greater than 1, that it's going to converge. But what I'm going to do is I'm going to use this comparison test. So the comparison test says you have a series, and I'll call this a sub k. You need to find another series to compare it to. So it seems logical to look at the series 1 over k to the 3 halves. And here I'm just getting rid of the plus 1. So I have a series to compare to mine. It's a p series. So I know it converges since P is 3/2. So I'm just going to make a comment that this is a convergent P series. The next thing I have to do is show which is the smaller and which is the larger. So since I'm using a convergent P series to compare, my goal is to show that A sub k is less than or equal to B sub k. And the 1 over k to the 3/2, that's my B sub k. Clearly that's true. Because if you look at your A sub k, we're adding 1 to the denominator. Look at your B sub k. If you're adding 1 to the denominator, and here we're only concerned with k values greater than or equal to 1, because that's where our series begins. So look at these positive k values. If you're adding 1 to the denominator, it's going to be larger than if you're looking at k to the 3/2. So the fraction as a whole, 1 over 3/2 plus 1, will be smaller than 1 over k to the 3/2. Picked a series, determined whether it converges or diverges, looked at which one was smaller, which one was larger, and now we're done. There's not a lot of work here, but we have to make a conclusion. So our series, so this series converges by comparison test. So we do have to state the test that we're using. Let's try another example. Part B, we look at a series from k is equal to 1 to infinity of natural log of k over k to the 4th. Again, I see the k to the 4th in the denominator, so I'm thinking 1 over k to the 4th is a P series that converges. I could probably use that as comparison. But I have that natural log of k. So what I'm going to do is I'm going to first deal with the natural log of k. And note that that's less than or equal to the function k. So let me illustrate what I mean here. And here we're starting with k is equal to 1. So natural log of k, starting at k is equal to 1, graph kind of looks like this. The graph of k is just a line diagonal passing through the origin. So I can see that k is larger than natural log of k. So my goal here is to build up this inequality so that I get my a sub k. All I have to do is divide both sides by k to the 4. Now k to the 4 is always going to be positive because it's to the 4th power, so I don't have to worry about flipping the inequality. And now I'm essentially done. K over k to the 4th is 1 over k to the 3rd. So my comparison series is going to be 1 over k to the 3rd, which is a convergent P series. And I've already showed which is the smaller and which is the larger. So at this time I can conclude that this series converges by the comparison test. So last example using this comparison test, I have 1 over natural log of k. Now it would be nice if this was just 1 over k, then it's harmonic and it's going to diverge. But here I do have a typo. This is supposed to start at k is equal to 2 because natural log of 1 is 0 and this would be undefined. So I'm going to go back to my natural log of k that I had in the previous example. So our natural log of k is going to be less than or equal to k. But I need 1 over natural log of k. Going back to our algebra, whenever you have fractions, you can flip them, but you have to flip your inequality. So I have this inequality that says 1 over natural log of k is greater than or equal to 1 over k. So my series, starting with 2, is going to be this harmonic series 1 over k, which is a convergent p-series, or you could just say it's harmonic. But you do have, oh, sorry, not convergent, it's a divergent. But you do have to state whether it diverges or converges. So divergent p-series, or you could just say divergent harmonic series. And we have our inequality, we have divergent. So this fits criteria 2 of the comparison test. I can conclude that my series diverges by comparison test. All right, let's look at our last test for convergence. This is going to be our limit comparison test. The advantage to using the limit comparison test is you don't have to show which is the smaller and which is the larger. However, you still have to find a series to compare to your given series. So in the limit comparison test, we have our two series, a sub k and b sub k. And we're going to take the limit as k goes to infinity of a sub k over b sub k. We're going to determine convergence by the limit we get. If the limit is between 0 and infinity, then both converge or diverge. If the limit is 0 and b sub k converges, then a sub k converges. If the limit is infinity, b sub k diverges, then a sub k diverges. Example 2a, we have our series sine of pi over k. I need to choose a series to compare it to. So typically what I do when I have trig functions, and this works most times, not always, is I'll just assign a series that is the argument on my trig function. So I'm going to use pi over k. So notice that I could pull out the pi because it's constant, and my series is simply 1 over k. 1 over k harmonic, it diverges. Multiplying it by pi does not change whether it converges or diverges. So you could say that it's divergent harmonic, divergent p-series. So now I just have to take the limit. I don't have to show which one is larger and which one is smaller. Going back to our growth rates, this falls under that limit for growth rates, where we determine which one grows faster, which one grows slower. So as k goes to infinity, this would be sine of pi over k over pi over k. Now that's going to be indeterminate. It's 0 over 0. So I'm going to use L'Hopital's. The derivative on the top would be chain rule. Derivative of sine is cosine. Argument stays the same times the derivative of pi over k. Now I'm not actually going to take the derivative because I know that the argument pi over k is the same as the pi over k in the denominator. So I know that when I take the derivative with respect to k of pi over k, it's going to be the same as the denominator, which is the derivative with respect to k of pi over k. So this is a trick we often do in calculus. And since these are the same values, I can cancel. I'm looking at the limit as k goes to infinity of cosine of pi over k. As k goes to infinity, it's cosine of 0, which is 1. So my limit is between 0 and infinity. I can conclude that both series either converge or both diverge. But since I know my comparison series diverges, I can conclude that the series diverges. So the series diverges by the limit comparison test. So this is the final example for the section. Again, this is a very short section. Notice that this series is a bit more complicated. There's a polynomial in the numerator and the denominator. So a trick we often do here is we just look at the first terms of numerator and denominator. So I'm going to ignore the plus 5, and this is k. The 2k to the third plus k minus 3, I'm going to ignore the k minus 3, because that allows us to write this series as 1 over 2k squared. Now notice that I could pull out my 1/2, and then I have a series that converges. So 1 over k squared is a convergent p-series. The half in the front does not change convergence or divergence. I have my comparison. Now I'm going to take the limit. When I take the limit, I want to use the 1 over 2 times k squared. That would be my b sub k. So our limit as k goes to infinity of k plus 5 over 2k to the third plus k minus 3 divided by 1 over 2k squared algebraically would just be multiplying by the reciprocal of the denominator to get k plus 5 over 2k to the third plus k minus 3, and I'm going to multiply that by 2k squared over 1. And then this is still going to be infinity over infinity. I'm going to go ahead and distribute in the numerator by multiplying k plus 5 by 2k squared to get 2k to the third plus 10k squared. So this looks much nicer. And my choice of comparison means that, and hopefully you notice this, that the first term in the numerator and denominator is the same. So I can see right away the limit's going to be 1. But I'm going to go through the algebra. And you could do this in a variety of ways. You could see that this is infinity over infinity. So you could use L'Hopital's a few times. But I'm just going to divide everything by the highest power k to the third to get the limit as k goes to infinity of 2 plus 10 over k over 2 plus 1 over k squared minus 3 over k to the third. And now taking the limit, all of these fractions will go to 0. So our limit as k goes to infinity of 2 over 2, that's just equal to 1. So this, like our previous example, fits the criteria of limit between 0 and infinity, so both converge or both diverge. In this case, my comparison is convergent, so my series will also converge. So this series converges, oops, can't spell, by the limit comparison test. That's it for this section. In the next section, we're going to be looking at 2 more tests for convergence or divergence of a series. Now again, remember, we're just determining whether it converges or diverges. In the event it converges, we're not actually finding what it converges to. So that's it.